The universe is broken. Not metaphorically, not philosophically, mathematically broken. We've measured something that should be impossible, an observation that violates the fundamental laws of physics, a number that cannot exist according to everything we know about reality. The observable universe, the total region of space we can see in all directions, is 93 billion light-years in diameter. That sounds big. It is big. But here's the problem. The universe is only 13.8 billion years old. Light travels at 299,792 kilometers per second. That's the cosmic speed limit, the absolute maximum speed at which anything, matter, energy, information, causality, can travel. Nothing goes faster, nothing can go faster. This is the bedrock of relativity, Einstein's unbreakable law. So let's do simple math. If the universe is 13.8 billion years old, and light has been traveling at maximum speed for that entire time, the farthest anything could possibly be from us is 13.8 billion light years. Multiply by 2, since light could travel that far in both directions from our position, and the observable universe should be at most 27.6 billion light-years in diameter. But it's not. It's 93 billion light-years. The universe is 3.4 times larger than the age of the universe and the speed of light allow. This is not a small discrepancy. This is not a measurement uncertainty. This is a factor of more than 3 violation of basic physics. Either our measurements are catastrophically wrong, and centuries of astronomy, cosmology, and physics are fundamentally broken, or something impossible happened in the early universe. Something that breaks every intuition you have about space, time, and causality. And I'm going to show you what that something is. The solution is even stranger than the problem, more mind-bending than the paradox, more extraordinary than anything science fiction has imagined. But first, you need to feel the full weight of how broken this is. This isn't some abstract cosmological curiosity. This isn't a minor inconsistency that specialists argue about in journals. This is about whether the fundamental laws of physics work. Because if the universe is bigger than it should be, bigger than the speed of light allows, then one of 3 things must be true. Option 1. The speed of light isn't constant. If light traveled faster in the past, or if the cosmic speed limit has changed over time, that would break Einstein's theory of relativity. It would invalidate GPS satellites. It would make nuclear reactors impossible. It would unravel essentially all of modern physics. We can rule this out. The speed of light is constant. We've tested it exhaustively. It doesn't change. Option 2. The universe's age is wrong. Maybe the universe isn't 13.8 billion years old. Maybe it's much older, 50 billion years, or 100 billion years, and we've miscalculated. We can rule this out too. We've measured the universe's age through multiple independent methods. The cosmic microwave background, the oldest stars, radioactive decay in meteorites, the expansion rate of space, they all agree. 13.797 billion years, give or take 23 million years. That's precise. That's confirmed. Option 3. Something else happened. Something that doesn't violate the speed of light, doesn't change the universe's age, but still explains how space got so impossibly large. Spoiler, it's option 3. And the explanation, cosmic inflation, is one of the most extraordinary, counterintuitive, mind-breaking ideas in all of science. It proposes that in the first tiny fraction of a second after the Big Bang, a span of time so short it's essentially zero, the universe expanded exponentially. Space itself doubled in size every 10 to the power of -37 seconds. The universe grew by a factor of at least 10 to the power of 26 in less time than it takes light to cross a proton. If that sounds insane, you're right. It is insane. But it's also the only explanation that makes the math work, and the evidence supporting it is overwhelming. But I'm getting ahead of myself. Before I explain the solution, you need to understand the problem. Deeply, viscerally. You need to feel how broken this observation is, because only then will you appreciate how radical the solution had to be. Here's where we're going. Act 1 is where we are now, confronting the impossible measurement. The universe is too big. This shouldn't be possible. Act 2 will establish what we expected to find based on the Big Bang and the speed of light. We'll do the simple calculation. 13.8 billion years. Light speed, basic physics. The universe should be 27.6 billion light years across, but it's not. We'll see exactly what we measured instead and why it shatters expectations. Act 3, we'll talk about the cosmic speed limit, why nothing can go faster than light, why this makes the universe's size impossible. We'll look at whether cosmic expansion can explain the discrepancy. Spoiler, it can't. Not fully. There's still a gap. Something else had to happen. Act 4 is where your brain breaks. We'll introduce cosmic inflation. The idea that in the first 10 to the power of -32 seconds after the Big Bang, the universe expanded faster than light by an enormous factor. Space itself grew exponentially. The universe went from smaller than a proton to larger than a galaxy in less time than it takes to blink. This sounds impossible because it defies every intuition you have. But it's the only explanation that works. Act 5, we'll look at the evidence. Why do we believe this happened? What observations support inflation? I'll show you 5 pieces of evidence, problems that inflation solves, predictions that match observations. By the end, you'll understand why cosmologists accept this wild idea. Act 6 is the payoff. What does this mean? If inflation happened, what does it imply about reality? About the size of the total universe beyond what we can see? About the possibility of other universes, bubble universes, eternal inflation, the multiverse? And what does it mean that we, tiny, temporary beings on a small planet, figured this out? This is going to challenge everything you think you know about space and time. The universe doesn't expand the way you think it does. Space doesn't behave the way you assume it does. The early moments of the Big Bang were stranger, exponentially stranger, than any physics textbook tells you. But stay with me, because by the end, you'll understand one of the most profound discoveries in the history of science. And you'll never think about the universe the same way again. Let's start with what we expected to find when we measured the size of the cosmos. The Big Bang happened 13.8 billion years ago. This is one of the most precisely measured numbers in all of cosmology. We know it to within 23 million years, less than 0.2% uncertainty. We know it from the cosmic microwave background, from the ages of the oldest stars, from the expansion rate of the universe. Multiple independent methods, all converging on the same number. 13.8 billion years. That's how long light has had to travel. That's how long the universe has existed. That's the absolute maximum time available for anything, including light, to cross space. So when we ask, how big is the observable universe? The answer should be straightforward. Light travels at a fixed speed. Time is finite. Distance equals speed. Times time. The math is simple. Elementary school arithmetic. But the answer, when we actually measured it, was wrong. Impossible. Broken. Let me show you what we expected, and then I'll show you what we found. And you'll see why cosmologists spent decades trying to figure out what the universe did in its first incomprehensibly brief moment that made the numbers work. Act 2. What we expected is what we found. Let's establish the foundation. How do we know the universe is 13.8 billion years old? This isn't guesswork. This isn't philosophical speculation. This is measurement. Precise, confirmed, verified measurement. The cosmic microwave background. In 1964, scientists discovered a faint microwave radiation coming from every direction in space. This is the afterglow of the Big Bang, light that was released 380,000 years after the universe began, when the cosmos cooled enough for atoms to form. We can measure the properties of this radiation with extraordinary precision. The WMAP satellite and the Planck satellite mapped it in exquisite detail. And from that data, we can calculate exactly when the Big Bang occurred. The answer: 13.797 billion years ago. The uncertainty? Plus or minus 23 million years. That's 0.17% uncertainty. That's measuring the age of a 50-year-old person to within 3 months. That's precise. The oldest stars. We can also age date the oldest stars in the universe by studying their composition and evolution. Stars burn through their fuel at predictable rates. Old stars have specific properties. They're depleted in certain elements, enriched in others. We can model their life cycles and calculate their ages. The oldest stars we've found? About 13.6 billion years old, slightly younger than the universe itself. Which makes sense. Stars couldn't form until after the Big Bang. The expansion rate. We can measure how fast the universe is expanding today, a value called the Hubble constant. Then we can run the expansion backward, like rewinding a video. If the universe is expanding now, it was smaller in the past. Keep rewinding, and eventually everything converges to a single point. When does that convergence happen? 13.8 billion years ago. Radioactive decay. Certain radioactive isotopes, like uranium-238 and thorium-232, were created in the cores of massive stars that existed early in the universe's history. These isotopes decay at known rates. By measuring the ratios of different isotopes in old meteorites and stars, we can calculate how long they've been decaying. The answer, again, about 13.8 billion years. Multiple independent methods, all converging on the same answer. The universe is 13.8 billion years old. This is one of the most well-established facts in cosmology. So now we have a number. A precise, confirmed, indisputable number. 13.8 billion years. That's how long the universe has existed. That's how long light has had to travel. Now let's do the math. Light travels at 299,792 kilometers per second. This is a constant. It doesn't change. It doesn't depend on the observer. It's the same everywhere in the universe, at all times. Einstein proved this in 1905. Every experiment since has confirmed it. The speed of light, denoted by the letter c, is the cosmic speed limit, the absolute maximum velocity for anything with mass, energy, or information. So let's calculate. How far can light travel in 13.8 billion years? Step 1. Convert years to seconds. 13.8 billion years multiplied by 365.25 days per year, multiplied by 24 hours per day, multiplied by 3,600 seconds per hour. equals 4.35 times 10 to the power of 17 seconds. That is 435 quadrillion seconds. Step 2. Multiply by the speed of light. 299,792 kilometers per second, multiplied by 4.35 times 10 to the power of 17 seconds, equals 1.30 times 10 to the power of 23 kilometers. That is 130 sextillion kilometers. Step 3. Convert to light years for easier comprehension. 1.30 times 10 to the power of 23 kilometers divided by 9.46 times 10 to the power of 12 kilometers per light year equals 13.8 billion light years. So light, traveling at maximum speed for 13.8 billion years, covers a distance of 13.8 billion light years. This is obvious. It's built into the definition of a light year. 1 light year is the distance light travels in 1 year. So in 13.8 billion years, light travels 13.8 billion light years. Now, we're sitting here on Earth, looking out in all directions. Light from distant objects has been traveling toward us since the early universe. The farthest we should be able to see, the most distant objects whose light has had time to reach us, is 13.8 billion light years away. And since we can look in all directions, the observable universe should be a sphere, with us at the center and a radius of 13.8 billion light years. Diameter of that sphere: 13.8 billion light years times 2 equals 27.6 billion light years. That's the simple answer. That's what basic physics predicts. The observable universe should be 27.6 billion light years across. Hold that number in your mind, 27.6 billion light years, because now I'm going to tell you what we actually measured. And you're going to see why cosmologists had a problem. When astronomers measured the distance to the farthest observable objects in the universe, they found something impossible. The most distant galaxies we can observe are not 13.8 billion light years away in light travel distance. Their present-day co-moving distance is about 46.5 billion light years. Let me say that again. The edge of the observable universe, the farthest distance from which light has reached us, is 46.5 billion light years in every direction. That makes the diameter of the observable universe 93 billion light years. Not 27.6 billion, not 30 billion, not even 50 billion. 93 billion light years. The universe is 3.37 times larger than it should be, based on its age and the speed of light. How do we know this? How do we measure distances to objects billions of light years away? Redshift. When objects move away from us, the light they emit gets stretched, shifted toward the red end of the spectrum. The faster they're moving, the more redshifted their light becomes. We can measure this redshift precisely, and from the redshift, we can calculate how far away the object is and how fast it's receding. The most distant galaxies have redshifts of ZE approximately 10 or higher. That corresponds to a distance of over 46 billion light years, standard candles. Certain astronomical objects, like type Ia supernova and Cepheid variable stars, have known intrinsic brightness. By measuring how bright they appear versus how bright they actually are, we can calculate their distance. It's like seeing a 100-watt light bulb and determining how far away it is based on how dim it looks. These measurements confirm the distances derived from redshift. The cosmic distance ladder. Astronomers use multiple methods at different scales: parallax for nearby stars, Cepheids for nearby galaxies, supernovae for distant galaxies, and redshift for the most distant objects. Each method calibrates the next. Each step on the ladder confirms the others. And they all agree. The observable universe is approximately 93 billion light-years across. This is not uncertain. This is not controversial. This is confirmed by multiple independent measurements. The observable universe has a radius of 46.5 billion light-years and a diameter of 93 billion light-years, but the universe is only 13.8 billion years old. Light has only had 13.8 billion years to travel. These numbers don't work. 93 billion divided by 27.6 billion equals 3.37. The universe is more than 3 times larger than physics allows. This should be impossible. Light cannot travel faster than light. So how did distant galaxies get 46.5 billion light-years away if light has only had 13.8 billion years to travel? What happened? Let me give you an analogy that captures how broken this is. Imagine you start running the moment you're born. You run at exactly 10 kilometers per hour. Not faster, not slower. Constant speed. You never stop. You run for 20 years straight. Simple math. How far from your starting point are you after 20 years? Distance equals speed times time. 10 kilometers per hour times 20 years times 365.25 days per year times 24 hours per day equals 1,752,000 kilometers. You should be 1.75 million kilometers from where you started. But when we measure your actual position, we find you're 6 million kilometers away. 6 million, not 1.75 million. That's 3.4 times farther than you should be. But you didn't run faster. We measured your speed constantly, and it was always 10 kilometers per hour. And the time didn't change. You ran for exactly 20 years, confirmed by multiple independent clocks. So how are you 6 million kilometers away? Something is broken. The math doesn't work. Reality has violated basic arithmetic. That's the universe's problem. Light didn't travel faster. We've confirmed the speed of light is constant. Time didn't change. We've measured the universe's age through multiple methods, and they all agree. But distant objects are 46.5 billion light-years away, 3.4 times farther than 13.8 billion years of light travel allows. Now, you might be thinking, wait, doesn't the universe expand? Can't that explain it? Good question. Let's talk about that. Because yes, the universe expands. Yes, that contributes to the size. But no, it doesn't fully explain the discrepancy. In fact, even accounting for expansion, the universe is still bigger than it should be. And that remaining gap, that unexplained extra distance, is where things get truly strange. You've just seen the problem laid out in stark, undeniable terms. Expected diameter, 27.6 billion light-years. Actual diameter, 93 billion light-years. Discrepancy, factor of 3.37. This shouldn't be possible. Light has a speed limit. Time is finite. The math should work, but it doesn't. Now, before we jump to the solution, before I tell you about cosmic inflation and the exponential expansion of space in the first fraction of a second, we need to address the obvious question. Can't the expansion of the universe explain this? After all, the universe is expanding. Galaxies are moving away from each other. Space itself is stretching. Surely that's why distant objects are farther than 13.8 billion light-years away, right? Partially. Yes. Expansion explains some of the discrepancy, but not all of it. Even accounting for the expansion of space over 13.8 billion years, the universe is still too big. There's a gap, an unexplained distance, a remaining impossibility. And to understand that gap, to see why we need something as radical as cosmic inflation, we need to talk about the cosmic speed limit, about what the speed of light actually means, about what it allows and what it forbids, and about the one weird loophole that makes the universe's impossible size possible. Let's talk about the speed limit of reality. Act 3. The speed limit of reality. Let's talk about the most fundamental rule in physics. Nothing can travel faster than light. This isn't just a speed limit like the one on a highway. This is a cosmic speed limit, an absolute maximum built into the fabric of reality itself. The speed of light, 299,792 kilometers per second, is denoted by the letter c in physics equations. And c isn't just fast, it's the maximum speed at which anything with mass, energy, or information can travel through space. Not very difficult to exceed, not impractical to reach, impossible to exceed. This comes from Einstein's special theory of relativity, published in 1905, and it's been tested exhaustively. Every particle accelerator experiment, every astronomical observation, every precision measurement, the speed of light is constant, and it's the cosmic speed limit. Why is it the maximum? Because as you approach the speed of light, strange things happen. Time slows down, distances contract. Your mass, your resistance to acceleration, increases. At exactly the speed of light, time stops completely. Distances shrink to zero, and your mass becomes infinite. To accelerate something with mass to the speed of light would require infinite energy, which is impossible, so nothing with mass can reach light speed, let alone exceed it. Even massless particles, like photons, the particles of light, travel at exactly c. Not faster, not slower, always exactly c. And here's the critical part. This isn't just about physical objects moving through space. It's about causality, about cause and effect. No signal, no information, no causal influence can propagate faster than light. If two events are separated by more distance than light can travel in the available time, they cannot influence each other. They are causally disconnected. This is bedrock physics, the foundation of relativity, the structure of space-time itself. Nothing goes faster than light. So when we say the observable universe is 93 billion light-years across, but the universe is only 13.8 billion years old, we have a problem. Because if nothing can travel faster than light, how did objects get 46.5 billion light-years away from us? The answer lies in a subtle but critical distinction. Objects can't move through space faster than light, but space itself can expand faster than light. Let me explain. In 1929, astronomer Edwin Hubble made one of the most important discoveries in the history of science. He observed that distant galaxies are moving away from us, and the farther away a galaxy is, the faster it's receding. This wasn't random motion. This was a pattern, a systematic relationship between distance and velocity. Hubble realized the universe is expanding. Space itself, the fabric of the cosmos, is stretching. And as space stretches, galaxies embedded in that space get carried along, moving apart from each other. Here's the critical insight. Galaxies aren't moving through space. Space between them is growing. Imagine dots painted on the surface of a balloon. As you inflate the balloon, the dots move apart. But the dots themselves aren't moving across the rubber surface. The rubber itself is expanding, carrying the dots with it. That's the universe. Galaxies are the dots. Space is the rubber. And the whole thing is expanding. This is important because it creates a loophole in the cosmic speed limit. Einstein's relativity says, nothing can move through space faster than light. But it does not say, space itself can't expand faster than light. Space isn't a thing that moves. It's the arena in which things move. And the arena itself can expand at any rate. This is allowed by general relativity, Einstein's theory of gravity, and space-time. In fact, general relativity predicts that space can expand or contract depending on the matter and energy it contains. So, galaxies can recede from us faster than the speed of light, not because they're moving through space faster than light, but because the space between us and them is expanding. Let's quantify this. Hubble's law. The relationship between distance and recession velocity is described by the Hubble constant, denoted h0. Current measurements put h0 at approximately 70 kilometers per second per megaparsec. What does that mean? It means for every megaparsec, 3.26 million light-years, of distance, a galaxy recedes 70 kilometers per second faster. A galaxy 10 megaparsecs away recedes at 700 kilometers per second. A galaxy 100 megaparsecs away recedes at 7,000 kilometers per second. A galaxy 4,300 megaparsecs away, 14 billion light-years, recedes at 300,000 kilometers per second, the speed of light. And galaxies farther than that? They recede faster than light. Not because they're moving through space faster than light, but because space between us is expanding so much that the recession velocity exceeds c. The most distant observable galaxies are receding at roughly 3 times the speed of light. This is allowed. This doesn't violate relativity. Space can expand as fast as it wants. So problem solved, right? The universe is bigger than 27.6 billion light-years because space has been expanding, carrying distant objects to greater distances than light alone could travel. We can see objects 46.5 billion light-years away because those objects were much closer when their light was emitted, and over 13.8 billion years, expansion stretched the space between us. Well, yes, partially. Expansion explains a lot, but not everything. Because when we do the detailed calculation, accounting for how fast the universe has been expanding over its entire history, we still get a number that's too small. Let me show you why. Here's where it gets technical. Bear with me. If the universe has been expanding at a constant rate since the Big Bang, we can calculate how far distant objects should be today. The Hubble constant tells us the current expansion rate, 70 kilometers per second per megaparsec. If expansion was always at this rate, we'd expect the observable universe to have a radius of about 14 billion light-years, slightly larger than 13.8 billion because expansion stretched the distance light traveled. But we measure 46.5 billion light-years, so constant expansion doesn't explain it. Okay, but the universe hasn't been expanding at a constant rate. The expansion rate has changed over time. Early universe, matter-dominated era. When the universe was young, it was dense with matter and radiation. Gravity from all that mass slowed the expansion. The universe was still expanding, but decelerating. During this phase, expansion was slower than today. Recent universe, dark energy-dominated era. About 5 billion years ago, dark energy, a mysterious, repulsive force, became the dominant component of the universe's energy density. Dark energy causes expansion to accelerate. The universe is now expanding faster and faster. So, the expansion history looks like this. Early universe, expanding but slowing down, matter and radiation dominated. Recent universe, expanding and speeding up, dark energy dominated. When cosmologists account for this variable expansion history, using detailed models based on general relativity and observations of the cosmic microwave, background, supernova, and galaxy distributions, they calculate the expected radius of the observable universe. The result? Approximately 42 to 44 billion light-years. That's larger than the simple 13.8 billion light-years. Yes, expansion stretches distances. But this result already assumes an early inflationary phase. Without inflation, standard Big Bang expansion alone cannot explain why regions now separated by 46.5 billion light-years were ever in causal contact. And when you account for the early deceleration due to matter and radiation, that gap gets bigger, not smaller. Because in the early universe, when expansion was slower, objects couldn't get as far apart as they would have if expansion had been faster. So the problem remains. The observable universe is still too large. Even with expansion, even accounting for the detailed history of how fast the universe has been stretching over 13.8 billion years, there's a missing piece, an unexplained component, something that happened in the early universe that front-loaded the size. That pushed objects incredibly far apart before normal expansion even began, and that something is cosmic inflation. Let me be precise about what the problem actually is. If you take the Big Bang model, the standard cosmological model based on general relativity, and you include the age of the universe, 13.8 billion years, the speed of light, constant at 299,792 kilometers per second, the expansion history, decelerating early, accelerating recently, the matter and energy content, baryons, dark matter, dark energy, radiation, and you calculate the size of the observable universe today, you get approximately 44 billion light-years in radius. That's the prediction. That's what the math says. But we measure 46.5 billion light-years in radius. The discrepancy is about 2.5 billion light-years, or roughly 5 to 6% of the total. Now, 5% doesn't sound like much, but in cosmology, where our models are precise and our observations are exact, a 5% unexplained discrepancy is huge. It's like calculating that a building should be 100 meters tall and measuring 105 meters. That extra 5 meters means something is wrong with your model. There's a force, a component, a phenomenon you didn't account for. In the universe's case, that missing component is early universe inflation. But here's the deeper issue. It's not just about getting the numbers to match. It's about understanding how the universe got so large so quickly. Because even if expansion accounts for most of the size, there's a timing problem. In the very early universe, within the first 380,000 years, regions of space that are now separated by billions of light-years were causally connected. They were close enough to exchange light and reach thermal equilibrium. We know this because the cosmic microwave background is uniform to 1 part in 100,000. Every direction has the same temperature. That means every region was in causal contact, able to exchange energy and equilibrate. But if the universe expanded at the standard rate from the Big Bang onward, those regions should never have been in causal contact. They should have been separated from the very beginning. So how did they equilibrate? The only answer: something happened before normal expansion began. Something that brought all observable regions into causal contact. Something that allowed them to equilibrate. And then something that pushed them incredibly far apart, incredibly fast. That something is cosmic inflation, a period of exponential expansion in the first tiny fraction of a second after the Big Bang, a phase where the universe doubled in size every 10 to the power of negative 37 seconds, where space expanded faster than light by an enormous factor. Inflation explains the size discrepancy. It explains the uniformity. It explains multiple problems that the standard Big Bang model can't solve. But it requires accepting something that sounds completely insane. Let me show you just how insane. You've just seen why the universe's size is a problem. Even accounting for expansion, even including the detailed history of how space has been stretching over 13.8 billion years, the observable universe is still too big, by about 5%, which doesn't sound like much until you realize that 5% represents billions of light years. Billions of light years that can't be explained by standard physics. And there's a second problem. The cosmic microwave background is too uniform. Regions that should never have been in contact somehow have the exact same temperature. Both problems point to the same conclusion. Something extraordinary happened in the very early universe. Something that pushed space apart faster than the normal expansion rate. Something that connected all observable regions before separating them. That something is cosmic inflation. And when I tell you what inflation proposes, when I show you the timescales and the expansion factors, your brain is going to reject it. Because inflation claims that in less than a trillionth of a trillionth of a trillionth of a second, the universe grew from smaller than an atom to larger than a galaxy. Space expanded faster than light, exponentially, doubling in size every 10 to the power of negative 37 seconds. This sounds like science fiction. It sounds impossible. It sounds like someone made up a solution to fit the data. But it's real. It happened. And the evidence is overwhelming. Let me show you how inflation works and why we believe it. Welcome to the most mind-bending explanation in all of cosmology. Act 4. The solution: cosmic inflation. In 1980, a young physicist named Alan Guth proposed something that sounded completely insane. He suggested that in the first incomprehensibly tiny fraction of a second after the Big Bang, a span of time so brief it's essentially zero, the universe underwent a period of exponential expansion. Not just expansion, exponential expansion. The universe doubled in size, then doubled again, then doubled again, over and over and over, on timescales on the order of 10 to the power of negative 37 seconds. The universe doubled in size again and again. That's 10 quadrillion, 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 quadrillionth of a second. A decimal point followed by 36 zeros and then a 1. This is so fast that the word fast doesn't capture it. This is exponential growth at a rate beyond human comprehension. To give you a sense of scale, if you started with a region of space the size of a proton, 10 to the power of negative 15 meters across, and you doubled it 90 times, how big would it be? Larger than the observable universe. One proton, doubling 90 times, becomes bigger than the entire cosmos we can see today. And inflation didn't just double the universe 90 times. It doubled it hundreds of times. Maybe thousands of times. We don't know exactly how many, but the minimum estimate is that the universe expanded by a factor of at least 10 to the power of 26. That's a 1 followed by 26 zeros. A region that was initially smaller than a proton, far, far smaller, expanded to a size larger than a galaxy in a fraction of a second, in 10 to the power of negative 32 seconds. Let me emphasize how absurd this timeline is. 10 to the power of negative 32 seconds is a decimal point followed by 31 zeros, and then a 1 second 100 millionth of a trillionth of a trillionth of a second, so short that light, traveling at maximum cosmic speed, would cross a distance smaller than a proton. In that incomprehensible instant, the universe went from quantum scale to cosmic scale. This sounds impossible. It sounds like someone made up a number to fix the data. It sounds like the kind of thing you'd dismiss as pseudoscience. But it's not. It's the only explanation that makes the observations work. And the evidence supporting it is overwhelming. Inflation is now the standard model of the early universe. It's taught in textbooks. It's accepted by the vast majority of cosmologists. Not because it's intuitive. It's not, but because it works. It solves multiple problems. It makes specific predictions, and those predictions match observations to extraordinary precision. But before we get to the evidence, let me show you exactly when inflation happened and what it did. Let's walk through the first moments of the universe, second by second, or rather, fraction of a second by fraction of a second. T equals 0. The Big Bang singularity. Technically, we can't say what happened at exactly t equals 0. Physics breaks down. Our equations produce infinities. Quantum mechanics and general relativity, the two pillars of modern physics, are incompatible at this scale. We don't know what happened at t equals 0, but we can describe what happened immediately after. T equals 10 to the power of negative 43 seconds, the Planck time. This is the earliest moment we can meaningfully talk about with current physics. Before this, quantum effects of gravity dominate, and we need a theory of quantum gravity, which we don't have yet. At the Planck time, the universe was unimaginably hot and dense. Temperature, 10 to the power of 32 Kelvin. Size, 10 to the power of negative 35 meters. All four fundamental forces were unified. T equals 10 to the power of negative 36 seconds. Inflation begins. Something triggered a phase transition in the universe. A quantum field, called the inflaton field, entered a high-energy state. This high-energy state drove exponential expansion. Space began doubling in size every 10 to the power of negative 37 seconds. T equals 10 to the power of negative 36 to 10 to the power of negative 32 seconds. The inflation era. For about 10 to the power of negative 32 seconds, though this number is uncertain. It might have been longer or shorter. The universe inflated exponentially. Every 10 to the power of negative 37 seconds, double in size. In just 10 to the power of negative 32 seconds, that's roughly 100 doublings, maybe more. A region, initially 10 to the power of negative 26 meters across, far smaller than a proton, expanded to 10 to the power of 4 meters across, 10 kilometers, or larger, or much larger, depending on how long inflation lasted. The observable universe today, 93 billion light-years across, originated from a patch of space smaller than the smallest thing you can imagine. T equals 10 to the power of negative 32 seconds. Inflation ends. The inflaton field decayed. It transitioned from its high-energy state to a lower energy state. The energy that had been driving inflation was released as matter and radiation. This is called reheating. The universe was suddenly filled with particles, quarks, electrons, photons, at incredibly high temperatures. After T equals 10 to the power of negative 32 seconds. Normal expansion begins from this point onward. The universe expanded according to standard Big Bang cosmology, still expanding but decelerating due to gravity. Much, much slower than during inflation. The entire inflation era, the exponential expansion that made the universe bigger than it should be, lasted about 10 to the power of negative 32 seconds. 100 millionth of a trillionth of a trillionth of a second. Everything that followed, the formation of atoms, stars, galaxies, planets, life, consciousness, civilization, All of that happened in the 13.8 billion years after inflation ended. But the size of the universe? That was determined in the first 10 to the power of negative 32 seconds. Inflation front-loaded the universe's size. It created the vast expanse we observe today in a flash of exponential expansion so brief and so extreme that it defies comprehension. And that is how the universe got bigger than it should be. Now, let's connect this back to our original problem. We expected the observable universe to be 27.6 billion light-years across, based on age and light speed. We measured 93 billion light-years across. Standard expansion explains some of this, bringing the expected size to about 44 billion light-years radius. But there's still a gap, about 5 to 6% unexplained. Inflation fills that gap. Here's how, before inflation, all of the matter and energy that would eventually become our observable universe was contained in a region smaller than a proton. This tiny region was causally connected. Every part could exchange light and energy with every other part. This region equilibrated. It reached a uniform temperature. All quantum fluctuations smoothed out. Mostly. We'll come back to the mostly later. During inflation, that tiny smooth region expanded exponentially. Points that were initially close together, able to exchange light signals, were suddenly separated by vast distances. Inflation pushed them apart faster than light could travel between them. After inflation ended, these regions were no longer in causal contact. They couldn't exchange signals anymore, but they retained the properties they had before inflation separated them. After inflation, normal expansion continued. Space kept stretching, but at a much slower rate. Objects that inflation had separated by enormous distances continued to drift apart, but now according to standard Hubble expansion. The key insight: by the time normal expansion began, distant regions were already far apart. Inflation had pre-separated them. So, when we calculate distances today, we need to account for 1. The distance inflation created, exponential expansion in first 10 to the power of negative 32 seconds. 2. The distance normal expansion added, 13.8 billion years of standard cosmology. When you add both components, you get 46.5 billion light-years radius, 93 billion light-years diameter. The math works, the observations match, the discrepancy disappears. Inflation explains why the universe is bigger than it should be, because it was bigger than it should be from the very beginning. Inflation made it that way. But here's the part that's still troubling you. How can space expand faster than light? Didn't we just spend Act 3 talking about how nothing can exceed the speed of light? Let me address that directly. Einstein's special relativity says, nothing can move through space faster than light. Notice the critical word, through. Objects moving through space, particles, planets, galaxies, are limited by the speed of light. But space itself is not an object moving through anything. Space is the stage, the arena, the fabric of reality. And general relativity, Einstein's theory of gravity and curved spacetime, allows space to expand or contract at any rate. There is no speed limit on the expansion of space itself. Think of it this way. Imagine 2 ants on a rubber sheet. The ants can crawl across the rubber at a maximum speed. Let's say 1 centimeter per second. That's their speed limit. But if you stretch the rubber sheet, the ants move apart faster than they could by crawling. The rubber itself is expanding, carrying the ants with it. The ants aren't violating their speed limit. They're still crawling at 1 centimeter per second relative to the rubber beneath them. But the rubber is stretching, so the distance between them grows faster than their crawling speed allows. That's inflation. Space is the rubber sheet. Particles, or regions of space, are the ants. The ants can't move through the rubber faster than light speed, but the rubber can stretch as fast as it wants. During inflation, space stretched exponentially. Regions that were initially close together were carried apart at speeds vastly exceeding the speed of light. But no information traveled faster than light. No signal. No causal influence. The regions simply became disconnected. Think about distant galaxies today. They're receding from us at 3 times the speed of light due to the expansion of space. Are they violating relativity? No, because they're not moving through space at that speed. Space between us and them is expanding. Inflation is the same principle, just much more extreme. Space didn't just expand, it expanded exponentially, doubling every 10 to the power of negative 37 seconds. This is allowed by general relativity. There's no law against it. Space can expand as fast as the physics of the inflaton field drives it to expand. And during inflation, that expansion rate was incomprehensibly, exponentially fast. So yes, the universe got bigger than the speed of light, and the age of the universe should allow. But not by violating the speed of light, by exploiting a loophole. Space itself can expand faster than light. Now, you might be wondering, what caused inflation? What was this inflaton field, and why did it suddenly start inflating the universe? Let me explain what we know, and what we don't know, about the cause of inflation. Here's where we need to be honest. We don't fully understand what caused inflation. We have models, we have proposals, we have mathematical frameworks that describe how inflation could work, but we don't have direct detection of the inflaton field or definitive proof of exactly what it was. Here's the leading hypothesis: the inflaton field. Inflation was driven by a quantum field called the inflaton. This is a hypothetical field, similar to the Higgs field, that permeates all of space. Fields in physics can have different energy states. The Higgs field, for example, settled into a particular energy state that gives particles their mass. The inflaton field, according to the theory, started in a high energy state called a false vacuum. In this false vacuum state, the inflaton field had enormous energy density. And in general relativity, energy density creates a kind of gravitational repulsion, the opposite of normal gravity. This repulsion drove exponential expansion. As long as the inflaton remained in the false vacuum, space expanded exponentially, the phase transition. At some point, after about 10 to the power of negative 32 seconds, the inflaton field underwent a phase transition. Like water freezing into ice, the field transitioned from the false vacuum to a lower energy true vacuum state. When this happened, the exponential expansion stopped. Inflation ended, reheating. The energy that had been stored in the inflaton field was released. It converted into matter and radiation, quarks, electrons, photons, all the particles that fill the universe. This energy dump heated the universe to incredibly high temperatures. This phase is called reheating. After reheating, the universe continued to evolve according to standard Big Bang cosmology. What we don't know: what exactly the inflaton field is. Is it a fundamental field? A composite? Related to other fields? What triggered the phase transition? Why did inflation start? Why did it end? How long inflation lasted? 10 to the power of negative 32 seconds is an estimate. It could have been longer or shorter. Whether there was one inflation event or multiple, could inflation happen more than once? What we do know: something like inflation happened. The evidence is too strong to ignore. The problems it solves are too significant. The predictions it makes match observations too precisely. We might not understand every detail of the inflaton field, but we know the universe underwent exponential expansion in its first moments, because the alternative, that the universe is 93 billion light-years across by chance without inflation, requires absurd fine-tuning and leaves multiple observations unexplained. Inflation is the best explanation we have, and the evidence supporting it is overwhelming. Let me show you that evidence. You've just learned about cosmic inflation, an exponential expansion in the first 10 to the power of negative 32 seconds after the Big Bang that grew the universe from smaller than a proton to larger than a galaxy. This sounds insane. It sounds like someone made up a crazy idea to fix a problem with the numbers. And if that's all inflation was, just a mathematical trick to make the universe's size work, then yeah, it would be suspicious. It would be unsatisfying. But inflation doesn't just solve the size problem. It solves multiple problems. Problems that seem completely unrelated. Problems that the standard Big Bang model can't explain. And inflation makes specific predictions. Predictions that we can test by observing the universe. And when we test those predictions, they match observations. Again and again and again. Inflation isn't just a fix. It's a theory with explanatory power and predictive success. So, let me show you the evidence. 5 pieces of evidence that confirm inflation happened. 5 problems that inflation solves. 5 predictions that match reality. By the end, you'll understand why cosmologists, despite how crazy inflation sounds, accept it as the best explanation for the early universe. Let's look at the evidence. Act 5. Implications and evidence. The first piece of evidence for inflation comes from a problem called the flatness problem, and it's one of the strangest coincidences in cosmology. Space, according to general relativity, can have curvature. It can bend. It can be shaped like a sphere, a saddle, or it can be flat like a sheet of paper. Positive curvature. Space curves like the surface of a sphere. If you draw a triangle on positively curved space, the angles add up to more than 180 degrees. Negative curvature. Space curves like a saddle. Triangles have angles that add up to less than 180 degrees. Flat, zero curvature. Space is like a flat plane. Triangles have angles that add up to exactly 180 degrees. Parallel lines stay parallel forever. So, which is our universe? We've measured it, using the cosmic microwave background, galaxy distributions, and other observations. The answer? Our universe is flat, to within 0.4% measurement uncertainty. Space has zero curvature. It's geometrically flat. Okay, so what's the problem? The problem is that flatness is unstable. If the universe starts out even slightly curved, even by 1 part in a trillion, that curvature grows over time. The universe either becomes more and more positively curved, eventually collapsing back on itself, or more and more negatively curved, expanding forever, becoming increasingly saddle-shaped. Flatness is like balancing a pencil on its tip. Any tiny deviation, and it falls over. Flatness doesn't last. It's an unstable equilibrium. So if the universe is flat today, 13.8 billion years after the Big Bang, how flat did it have to be at the beginning? The calculation is terrifying. For the universe to be flat today to within 0.4%, it had to be flat 1 second after the Big Bang to within 1 part in 10 to the power of 15. That's 1 part in a quadrillion. Absurdly precise. And if you go back even further, to the Planck time, 10 to the power of negative 43 seconds after the Big Bang, the universe had to be flat to within 1 part in 10 to the power of 60. That's 1 followed by 60 zeros. A number so precise it's essentially impossible. Why would the universe start out that flat? What fine-tuned the initial conditions to such ridiculous precision? Without an explanation, this is just a cosmic coincidence, an unexplained piece of luck. But inflation solves it. Here's how. Imagine a small, wrinkled balloon. The surface has bumps and curves. It's not flat at all. Now inflate that balloon. Make it huge. Exponentially huge. What happens to the wrinkles? They get stretched out, smoothed over. The surface becomes flatter and flatter as the balloon expands. By the time the balloon is enormous, any small patch of its surface looks perfectly flat, even though globally it might still be curved. That's what inflation did to the universe. Even if the universe started with significant curvature, inflation stretched it so much that the curvature became negligible. Any initial wrinkles were smoothed out by exponential expansion. After inflation, the universe was essentially flat. Not because it started flat, but because inflation made it flat. And then, normal expansion continued from that nearly flat starting point, preserving the flatness we observe today. Inflation predicts the universe should be flat. We observe a flat universe. That's evidence number 1. The second piece of evidence comes from an even more disturbing observation, the cosmic microwave background. The CMB is the afterglow of the Big Bang. It's light that was released 380,000 years after the universe began, when the cosmos cooled enough for atoms to form. We can see this light in every direction. It fills the entire sky. And when we measure its temperature in different directions, we find something remarkable. The CMB has the same temperature everywhere. To within 1 part in 100,000, every direction in the sky has the same temperature, 2.725 Kelvin. This uniformity is extraordinary. It means the early universe was incredibly smooth. Every region had equilibrated, reached the same temperature and density. But here's the problem. For regions of space to equilibrate, to reach the same temperature, they need to be in causal contact. They need to be close enough to exchange light, heat, and energy. So let's ask, were all the regions we see in the CMB ever in causal contact? Let's calculate. 380,000 years after the Big Bang, when the CMB was emitted, light had only had time to travel 380,000 light years. That means the maximum distance over which regions could have equilibrated, called the horizon distance, was about 380,000 light years. Any regions farther apart than that had never exchanged light. They were causally disconnected. Now, look at the CMB in the sky. Pick 2 points separated by more than 2 degrees. When we trace the light from those 2 points back to the early universe, we find they come from regions that were separated by more than the horizon distance. Those regions were never in causal contact. Light couldn't travel between them. They couldn't have exchanged energy or equilibrated. So, how do they have the same temperature? It's like finding 2 isolated islands on opposite sides of the planet that both have exactly the same language, culture, and technology, despite never having any contact with each other. That shouldn't happen. It's a cosmic coincidence that demands explanation. Without inflation, there is no explanation. You just have to accept that causally disconnected regions happen to start with the same temperature. By accident, by luck. But inflation solves it. Here's how. Before inflation, all the regions that would eventually become our observable universe were packed into a tiny volume, smaller than a proton. At that scale, they were in causal contact. Light could travel between them. They could equilibrate. They could reach the same temperature. Then, inflation happened. Space expanded exponentially. Those regions that had equilibrated were suddenly pushed far apart, separated by distances vastly exceeding the horizon. After inflation ended, those regions were no longer in causal contact, but they retained the properties they had before inflation separated them. So, when we observe the CMB today, we see uniform temperature, not because distant regions somehow communicated after the Big Bang, but because they were in contact before inflation and retained that uniformity afterward. Inflation predicts the CMB should be uniform across the sky. We observe uniform CMB temperature. That's evidence number 2. The third piece of evidence comes from something we don't observe: magnetic monopoles. Let me explain what those are and why their absence is evidence for inflation. In electromagnetism, magnets always have 2 poles, north and south. Cut a magnet in half, and you get 2 smaller magnets, each with a north and south pole. You can never isolate a single pole, but particle physics theories, specifically grand unified theories, GUTS, that try to unify the electromagnetic, weak and strong forces, predict the existence of magnetic monopoles. These would be particles with only one magnetic pole, a north pole with no south, or vice versa. And according to GUTS, magnetic monopoles should have formed in the very early universe, within the first 10 to the power of negative 35 seconds, when temperatures were high enough for the forces to be unified. The problem? GUTS predict monopoles should be abundant. There should be roughly as many magnetic monopoles as protons in the universe. They should be everywhere, in rocks, in the ocean, in space. Detectors should be finding them constantly. The observation: we have never detected a single magnetic monopole, despite decades of searching with extremely sensitive detectors. 0. None. They don't seem to exist, or they're so rare we've never encountered one. So either 1. GUTS are wrong. Possible, but they're elegant theories that explain a lot. 2. Monopoles were created but somehow disappeared. How? 3. Monopoles exist but are incredibly rare. Why? Inflation provides option number 3. Here's how. Monopoles formed before inflation, in the first 10 to the power of negative 36 seconds, when the universe was incredibly hot and dense. At that point, monopoles were abundant. Maybe 1 per proton, just as GUTS predict. Then inflation happened. Space expanded by a factor of 10 to the power of 26 or more, exponentially, in 10 to the power of negative 32 seconds. The monopoles, which had been densely packed, were suddenly spread across an enormous volume. Inflation diluted them, stretched them out, made them incredibly rare. After inflation, the average distance between monopoles became larger than the observable universe. So, our entire observable region, 93 billion light-years across, might contain 0 monopoles, or maybe 1, but certainly not billions. The monopoles didn't disappear. They're still out there. But inflation made them so rare that we'd never expect to detect one in our cosmic neighborhood. Inflation predicts magnetic monopoles should be undetectable. We observe no magnetic monopoles. That's evidence number 3. Now, we get to the strongest evidence for inflation. The piece of data that convinced most cosmologists that inflation really happened. It comes from tiny imperfections in the cosmic microwave background. I told you earlier that the CMB is uniform to 1 part in 100,000. That's true, but it's not perfectly uniform. There are tiny temperature fluctuations, tiny hot spots and cold spots, variations of about 0.00001 degrees. These fluctuations are incredibly important. They're the seeds of all cosmic structure. Regions that were slightly denser than average collapsed under gravity to form galaxies, stars, and planets. Regions that were slightly less dense became cosmic voids. Everything we see in the universe today, every galaxy cluster, every star, every planet, grew from those tiny fluctuations in the CMB. So, where did those fluctuations come from? Inflation says they came from quantum mechanics. Here's the idea. During inflation, space was expanding exponentially. But at the quantum level, space is never perfectly smooth. Quantum mechanics introduces random fluctuations, tiny variations in energy density. Normally, quantum fluctuations happen at subatomic scales and don't affect macroscopic objects. But during inflation, something extraordinary happened. Quantum fluctuations got stretched to astronomical sizes. A quantum fluctuation that started at 10 to the power of negative 35 meters, the Planck scale, was inflated to 10 to the power of 6 meters, 1,000 kilometers, or larger. Microscopic became cosmic, and these stretched quantum fluctuations became the temperature variations we see in the CMB. Now here's the key. Inflation makes a specific prediction about these fluctuations. If they come from quantum mechanics during inflation, they should have a particular pattern. The fluctuations should be scale invariant, meaning they should look similar at all size scales. Whether you're looking at fluctuations on the scale of 1 degree in the sky, or 0.1 degrees, or 0.01 degrees, the statistical properties should be the same. This is called a Harrison-Zeldovich spectrum, or scale invariant spectrum, so we tested it. In the 1990s and 2000s, satellites like COBE, WMAP, and Planck mapped the CMB fluctuations with incredible precision. And what did they find? The fluctuations are scale invariant, almost perfectly. The spectrum matches inflation's prediction to within a few percent. This is extraordinary. Inflation, a theory about exponential expansion in the first 10 to the power of negative 32 seconds, makes a specific testable prediction about the pattern of temperature fluctuations in the CMB. And the prediction is correct. Not only that, but inflation predicts the fluctuations should be adiabatic, meaning they represent variations in both matter and radiation together, not one without the other. That's also what we observe. Inflation predicts the fluctuations should be Gaussian, following a particular statistical distribution. That's what we observe. Inflation predicts there should be slightly more power on large scales than on small scales, a small deviation from perfect scale invariance. That's what we observe. Every detailed prediction inflation makes about the CMB fluctuations matches observation. This is why cosmologists take inflation seriously. It's not just that inflation solves problems, it makes predictions. Specific, testable, falsifiable predictions. And those predictions turned out to be correct. That's evidence number 4. And it's the strongest evidence we have. The 5th piece of evidence is the one we're still searching for. It hasn't been confirmed yet, but if we find it, it will be the smoking gun. The definitive proof that inflation happened. It involves primordial gravitational waves. During inflation, space didn't just expand, it also vibrated. Quantum fluctuations in the fabric of space-time itself created gravitational waves, ripples in the geometry of space. These primordial gravitational waves would have left a specific imprint on the cosmic microwave background. Normal CMB fluctuations create a pattern called E-mode polarization. This is what we've already detected. But gravitational waves from inflation would create an additional pattern called B-mode polarization. B-modes are a distinct signature. They're a swirl pattern in the polarization of the CMB light, and they can only be produced by gravitational waves from the very early universe. If we detect primordial B modes, it's game over. Inflation is confirmed. No other explanation can produce that signal. What if we don't find them? That doesn't disprove inflation. It just means the gravitational wave signal is weaker than current experiments can detect. Some inflation models predict strong signals, others predict weak ones. But if we do find them, that's the holy grail: direct detection of gravitational waves from 10 to the power of negative 32 seconds after the Big Bang. Confirmation that inflation happened, and potentially information about the energy scale and mechanism of inflation. It would be one of the greatest discoveries in the history of science. So that's evidence number 5. Still being searched for, but if detected, it would be definitive proof of inflation. You've just seen 5 pieces of evidence for inflation. Evidence number 1, the universe is flat, explained by inflation stretching out curvature. Evidence number 2, the CMB is uniform, explained by regions being in causal contact before inflation. Evidence number 3, no magnetic monopoles, explained by inflation diluting them to undetectable densities. Evidence number 4, CMB fluctuations match inflation's predictions, the strongest evidence, confirmed by multiple satellites. Evidence number 5, primordial gravitational waves, still being searched for, would be definitive proof. Inflation isn't just a fix for the universe's size, it's a comprehensive theory that solves multiple problems and makes testable predictions. And the predictions match observations. This is why cosmologists accept inflation despite how crazy it sounds. Because it works. The math works. The observations match. The theory is successful. But accepting inflation means accepting some truly wild implications about the nature of reality. If inflation happened, if space really expanded exponentially in the first 10 to the power of negative 32 seconds, then what does that mean for the universe beyond what we can see? What does it mean for the total universe? For regions beyond our observable bubble? And if inflation is eternal, if it never fully stops everywhere, what does that mean for the existence of other universes? Welcome to the deepest implications of cosmic inflation, the philosophical consequences, the existential questions. Let's explore what inflation means for reality itself. Act 6. What this means for reality. So inflation happened. The evidence is overwhelming. The universe expanded exponentially in the first 10 to the power of minus 32 seconds, growing from subatomic to cosmic in an incomprehensible flash. This explains why the observable universe is 93 billion light-years across, instead of 27.6 billion. It solves the flatness problem, the horizon problem, the monopole problem. It predicts the CMB fluctuations we observe. Inflation works. It's real. It happened. But now comes the truly mind-bending implication. What we can see, the entire observable universe, 93 billion light-years across, is just a tiny bubble in a vastly larger inflated space. Let me explain. Inflation expanded a region of space by a factor of at least 10 to the power of 26, probably much more. Maybe 10 to the power of 100 or higher. We don't know exactly. But let's be conservative and say 10 to the power of 26. That means a region that was initially 10 to the power of minus 26 meters across, far smaller than a proton, expanded to 10 to the power of 0 meters, 1 meter, by the time inflation ended. Then normal expansion continued for 13.8 billion years, stretching that 1 meter region to 93 billion light-years, the size of our observable universe. But here's the key. That's just the region that became our observable universe. The total inflated region, the entire volume that underwent inflation, is much larger. How much larger? If inflation expanded space by 10 to the power of 26, and our observable universe came from a region 10 to the power of minus 26 meters across, then the total inflated region could be at least 10 to the power of 26 meters across. That's 10 billion light years before normal expansion. After 13.8 billion years of expansion, that region would now be incomprehensibly vast, far, far larger than what we can observe. We're talking about a region at least 10 to the power of 23 times larger than the observable universe. Maybe 10 to the power of 100 times larger. Maybe infinitely large if inflation expanded space to infinite size. Our observable universe, everything we can see, measure, or ever hope to reach, is just one tiny bubble in an unimaginably larger inflated cosmos. Think about that. Every galaxy, every star, every planet, every person who has ever lived, everything you can see with the most powerful telescopes, the entire cosmic microwave background, the entire 93 billion light-year sphere of observable space. That's just a small patch of the total universe, a bubble, a local region, one tiny corner of something vastly larger. Beyond the edge of our observable universe, beyond the cosmic horizon, space continues. More galaxies, more stars, more structure, potentially infinite. But we can never see it. We can never reach it. Light from those regions will never reach us because the expansion of space carries them away faster than light can travel. We are isolated, trapped in our bubble. The observable universe is our cosmic prison, not because of walls, but because of the speed of light and the expansion of space. And our bubble? It's microscopic compared to the total inflated volume. But wait, it gets stranger. Most models of inflation predict something even more extraordinary: eternal inflation. Here's the idea. Inflation doesn't end everywhere at once. It's a quantum process. Different regions of space undergo the phase transition, the end of inflation, at different times. In some regions, the inflaton field decays quickly. Inflation stops. Space returns to normal expansion. Matter and radiation form. That region becomes a bubble universe. But in other regions, the inflaton field stays in its high-energy state. Inflation continues. Those regions keep expanding exponentially. And within those still inflating regions, more bubble universes form. Each bubble is a region where inflation ended and normal physics took over. This process never fully stops. Somewhere in the vast inflated space, inflation is always continuing. New bubbles are always forming. This is eternal inflation, and it has a stunning implication: the multiverse. Our observable universe is one bubble, one region where inflation ended 13.8 billion years ago. But there are other bubbles, infinite bubbles, each one a separate universe with its own 93 billion light-year observable region, its own galaxies, its own stars. Each bubble is causally disconnected from the others. Light cannot travel between bubbles. They are separate realities. And here's the truly wild part. Each bubble might have different physical laws. The inflaton field's decay, the way it transitions from false vacuum to true vacuum, might be random. Quantum fluctuations might determine the final state. So different bubbles might have different values of physical constants, different strengths of fundamental forces, different particle masses, different numbers of dimensions. Some bubbles might have physics that allows stars, planets, and life. Others might not. Most might be sterile, empty, or hostile to structure formation. We exist in a bubble with physics that allows us to exist, not because our bubble is special, but because we can only observe bubbles compatible with our existence. This is the anthropic principle. So the multiverse, infinite bubble universes with potentially different laws, is a natural consequence of eternal inflation. Can we ever test this? Can we ever detect other bubbles? Probably not. Bubbles are causally disconnected. We can't see them. We can't reach them. We can't communicate with them. Some physicists argue this makes the multiverse unscientific. If we can't test it, it's not science, it's philosophy. Others argue that inflation predicts eternal inflation and bubble universes as a natural consequence. We don't have to observe other bubbles to accept that they exist, just as we accept that distant galaxies beyond our cosmic horizon exist, even though we'll never see them. This is controversial, contentious, debated among cosmologists, but it's a consequence of inflation, and inflation is supported by evidence. So, if we accept inflation and the evidence is strong, we might have to accept the multiverse as well, whether we like it or not. Now here's the irony, the twist, the uncomfortable truth that cosmologists don't like to talk about. Inflation solves fine-tuning problems. The flatness problem required the universe to start with absurd precision, 1 part in 10 to the power of 60. Inflation explains that without fine-tuning initial conditions, but inflation itself requires fine-tuning. The inflaton field had to have precisely the right properties for inflation to work. Too much inflation, the universe becomes too smooth. Quantum fluctuations get stretched and diluted so much that there are no density variations, no seeds for galaxies, no structure, just empty, perfectly uniform space. Too little inflation doesn't solve the flatness and horizon problems, doesn't explain why the universe is bigger than it should be, just right. Enough inflation to make the universe flat and uniform, but not so much that structure disappears. Just enough quantum fluctuations to seed galaxies, but not so much that the universe is chaotic. This just right condition requires the inflaton field to have specific properties. The potential energy curve has to be shallow enough for slow roll inflation. The field has to start in the right initial state. The phase transition has to happen at the right time. The energy scale has to be within a narrow range. If any of these parameters were significantly different, inflation either wouldn't happen or would produce a universe incompatible with structure and life. So, we've replaced one fine-tuning problem with another. Why does the inflaton field have the properties it has? Possible answers. 1. Lucky chance. The inflaton just happened to have the right properties. We won the cosmic lottery. 2. Anthropic principle. Maybe many bubbles exist with different inflaton properties. Most produce sterile universes. We exist in one of the rare bubbles where inflation worked correctly, because only those bubbles allow observers. 3. Deeper theory. Maybe there's a more fundamental theory, quantum, gravity, string theory, something else, that predicts the inflaton's properties without fine-tuning. We don't know. This is an open question. Inflation solves some mysteries but raises others. It pushes the fine-tuning problem back one level. This doesn't mean inflation is wrong. It just means we don't have the complete story yet. Inflation explains observations. It makes predictions. It's our best model of the early universe. But it's not the final answer. There's more to discover, deeper questions to ask, and that's okay. That's how science works. Each answer leads to new questions. Each solution reveals new mysteries. Inflation is extraordinarily successful, but it's not the end of cosmology. It's a milestone on a longer journey. Let's be honest about what we don't know, about the gaps in our understanding, about the questions inflation leaves unanswered. Question 1. What exactly is the inflaton field? We have models, we have proposals, scalar fields with specific potentials, but we don't have direct detection. We don't know if the inflaton is a fundamental field, a composite object, or related to other known fields like the Higgs. Question 2. What triggered inflation to start? Why did the inflaton field enter its high-energy false vacuum state? What caused the phase transition? Was it random? Inevitable? Triggered by some earlier event? We don't know. Question 3. What caused inflation to end? Why did the inflaton decay? What determined the timing? Why did it happen when it did, and not earlier or later? We have models of phase transitions, but no definitive answer. Question 4. Did inflation happen once or multiple times? Could there have been multiple periods of inflation? Could inflation happen again in the future? Is our bubble universe's inflation truly over, or could it restart? We don't know. Question 5. Is eternal inflation real? Do bubble universes actually exist? Is the multiverse real? Or is it just a mathematical artifact of our models? We can't test this directly. It might be untestable. This troubles many physicists. Question 6. Why do the physical constants have the values they do? If different bubbles have different constants, is there a deeper reason our bubble has the specific values we observe? Or is it pure anthropic selection? Unsatisfying, but maybe unavoidable. Question 7. What came before inflation? Did time exist before inflation? Was there a pre-inflation state? A multiverse that preceded our inflating region? Or does before inflation not even make sense? We're at the edge of physics here. General relativity breaks down. Quantum gravity is needed. We don't have that theory yet. These are profound questions, and we don't have answers. But here's what we do know. Something like inflation happened. The evidence is too strong to dismiss. The universe is 93 billion light-years across, not 27.6 billion. Inflation explains that. The universe is flat. Inflation explains that. The CMB is uniform. Inflation explains that. The CMB fluctuations match inflation's predictions. Precisely. We don't understand every detail. We don't know the complete mechanism. But we know inflation, or something functionally equivalent, occurred in the first moments after the Big Bang. And that knowledge, even incomplete, is extraordinary. Because 50 years ago, we didn't know any of this. We didn't know the universe was bigger than it should be. We didn't know about the flatness problem or the horizon problem. We didn't have the CMB data that confirms inflation. We've learned so much, and there's more to discover. The universe keeps revealing its secrets, slowly, one observation at a time, one theory at a time. And we're here, conscious beings on a small planet in one bubble universe, piecing it together. That's incredible. Let's zoom out. Let's see the full journey we've taken. We started with an impossible observation. The universe is 93 billion light-years across, but only 13.8 billion years old. Simple math said this was impossible. Light speed is finite. Time is finite. The universe should be 27.6 billion light-years across, but it's not. It's 3.4 times larger. We explored whether expansion could explain it. Partially, yes. But even accounting for the universe's expansion history, there was still a gap. Still an unexplained 5 to 6%. Then we learned about cosmic inflation, an exponential expansion in the first 10 to the power of minus 32 seconds after the Big Bang. space doubling every 10 to the power of minus 37 seconds. A region smaller than a proton, growing to larger than a galaxy in an incomprehensible flash. This sounds insane, but it's the only explanation that works. And inflation doesn't just solve the size problem. It solves 5 problems. 1. Flatness. Why the universe is geometrically flat. 2. Horizon. Why the CMB is uniform across causally disconnected regions. 3. Monopoles. Why we don't observe magnetic monopoles despite theoretical predictions. 4. CMB fluctuations. The pattern and amplitude match inflation's predictions. Precisely. 5. Gravitational waves, if detected, would be definitive proof. The evidence is overwhelming. Inflation happened, and the implications are profound. The observable universe is a tiny bubble in a vastly larger inflated space. Eternal inflation may create infinite bubble universes, a multiverse. Our bubble might be one of infinite bubbles with different physical laws. We exist in a bubble compatible with our existence, anthropic principle. This is humbling. Our observable universe, everything we can ever see, is just one tiny region in something unimaginably larger. But it's also extraordinary because we figured this out. We're conscious beings on a small planet, orbiting an average star, in one galaxy among trillions, in one bubble among possibly infinite bubbles. And we used telescopes, mathematics, and centuries of careful observation to deduce what happened 10 to the power of minus 32 seconds after the Big Bang. We reconstructed the universe's infancy. We tested predictions. We confirmed the theory. The universe is bigger than it should be. Not because physics is broken, but because we didn't understand the physics of the early universe. Inflation taught us that space can expand exponentially, that quantum fluctuations can become cosmic structure, that the observable universe is just a bubble in something far grander. Reality is stranger than we imagined, but it's also comprehensible, and that, the fact that we can comprehend it, is the most extraordinary thing of all. The universe is bigger than it should be, but should be assumed we knew the rules. We didn't. The universe taught us we were wrong. And that's not a failure. That's discovery. That's science. That's the human endeavor at its best. The universe is vast, ancient, strange, incomprehensible in scope. But we're here, asking questions, finding answers, understanding reality one observation at a time. And that makes us tiny, brief, fragile, part of something magnificent. Let's recap the journey. The paradox: the observable universe is 93 billion light-years across, but the universe is only 13.8 billion years old. Simple math says it should be 27.6 billion light-years across. The discrepancy: 3.4 times larger than physics allows. The solution: cosmic inflation. Exponential expansion in the first 10 to the power of minus 32 seconds after the Big Bang. Space grew by a factor of at least 10 to the power of 26, doubling every 10 to the power of minus 37 seconds. The evidence: 1. Flatness problem solved. 2. Horizon problem solved. 3. Monopole problem solved. 4. CMB fluctuations match predictions. 5. Gravitational waves, still searching. The implications: observable universe is a tiny bubble in vast inflated space. Eternal inflation may create infinite bubble universes. Multiverse is a natural consequence of inflation. We exist in a bubble compatible with life. The honest truth: we don't know all the details, but we know inflation, or something like it, happened. If this changed how you see the universe, if you'll never think about the Big Bang the same way, There are more impossible physics problems to explore, more paradoxes that shatter intuition, more discoveries that reveal reality's strangeness. Comment below. Which piece of evidence convinced you? The flatness problem? The horizon problem? The CMB fluctuations? Or are you still skeptical? Tell me where you stand. Share this video with someone who thinks they understand the Big Bang. They don't. Nobody does until they learn about inflation. And tonight, or right now, take a moment to think about what this means. You're in a bubble, a 93 billion light-year bubble in something vastly larger, maybe infinitely larger. Everything you can see, every star, every galaxy is confined to this one bubble. Beyond the edge, space continues. Other regions, other bubbles, other universes maybe. You'll never reach them. Light from them will never reach you. You're isolated, trapped by the speed of light and the expansion of space. But you're also aware, conscious, capable of understanding that you're in a bubble. And that awareness, that ability to comprehend cosmic inflation, exponential expansion, the multiverse, is extraordinary. The universe is bigger than it should be, but reality doesn't ask permission. It doesn't care about our intuitions or our expectations. The universe is what it is: strange, vast, magnificent. And we're here for this brief cosmic moment to understand it. Look up tonight. Remember, you're in a bubble. And let that humility and wonder change how you see everything.